Valeria Vignudelli, and I'm going to talk about monads and quantitative equational theories for non-determinism and probabilities. The results I'm going to present are based on collaborations with Matteo Mio, with Filippo Bonchi and Anna Skolva. We are interested in programs that combine together non-determinism and probabilities. And you can see here an example of such a program using a transition system semantics. And as you can see here, we have a state X that can non-deterministically choose between two different transitions. And these transitions actually reach probability distributions over states. If we take the left-hand transition, we have a probability distribution assigning probability 1/2 to x1 and probability 1/2 to x2, and with the right-hand transition, we reach x3 with probability 1/3 and x4 with probability 2/3. So, we represent the combination of non-determinism and probabilities via transitions that reach sets of probability distributions. And the fundamental problem in program semantics is verifying whether two programs are equivalent. And when we have two programs that have probabilistic information, we can actually have a final look at program equivalence and talk about program distances. As you can see here, we have two programs, and the second one has a possibly small variation given by epsilon in the probabilities, and in this case we would like to say that the two programs are not just not equivalent, but they are at the given distance possibly bounded by epsilon. And so this means that we want to talk about metrics or distances on sets of probability distributions. And moreover, since we are talking about computational effects such as non-determinism, probabilities and their combination, we want to model these computational effects using monads and also exploit the correspondence between monads and equational theories. And when we study program distances, this means talking about monads on metric spaces and quantitative equational theories. So in this talk I will try to tell you about all this by focusing in particular on the case when we have programs combining non-determinism and probabilities. So let me start by recalling monads and their correspondence with equational theories. When we have a monad in the category of sets, so given by a functor, a unit and a multiplication, we sometimes can find a corresponding equational theory defined in the usual sense of universal algebra, so given by a signature and a set of axioms. And formally this means that the equational theory gives a presentation of the monad, that is to say that we have an isomorphism of categories between on one side the category of Eilenberg-Moore algebras for the monad, which is a category of algebras defined indeed in categorical terms, and on the other side, the category of algebras or models, in the usual sense of universal algebra, of the equational theory. And when we have such a presentation, and so such an isomorphism, we can derive interesting results, such as the fact, for instance, that given a generating set X, the set of elements given by the monad over X is actually isomorphic to the set of terms induced by X and the signature of the equational theory modulo the axioms of the equational theory. But let me give you some example, and let's start from the case when the computational effect we are considering is non-determinism. And as you can see here, when we have a non-deterministic program, we have transitions that reach sets of states. For instance, here X reaches the set of states given by x1 and x2. And indeed we can model this computational effect using the power set monad, which assigns to a set X the set of non-empty finite subsets of X. And we have an equational theory, which is a presentation of the power set monad, and it is the equational theory of semilattices. This theory has one binary operation, this non-deterministic plus, representing union of sets, and as axioms, associativity, commutativity, and idempotency for this operation. Another example is given by probabilities. So when we have a probabilistic system, we have transition reaches probability distributions over states, and indeed we can model this computational effect using the distribution monad, which assigns to a set X the set of probability distributions on X which are finitely supported, so that assign a non-zero probability only to a finite number of elements of X. And again, we have a corresponding equational theory, so an equational theory presenting this monad, which is the equational theory of convex algebras. This theory has infinitely many binary operations as signature, this plus p for any p strictly in 0, 1, which denote distribution assigning p to the left-hand side and y minus p to the right-hand side. And as axiom, we have the probabilistic versions of associativity, commutativity, and idempotencies for these binary operations. And now the question is, what happens when we want to combine together non-determinism and probabilities? So what is the monad that we have, and what is an equational theory for reasoning about non-determinism and probabilities? Well, to answer this, let's go back to our example. So as we said, when we have programs combining non-determinism and probabilities, we have transitions, reaches sets of probability distributions. But we have, however, a problem here because the combination of the power set monad and the distribution monad, which would indeed give us sets of probability distribution, is not itself a monad. This is a well-known result from Baraka's PhD thesis, and we have, however, a solution, which is to use convex sets of probability distributions. Indeed, as we'll see, this gives us a monad. A set of probability distributions is convex if whenever we have two probability distributions in the set, then the set also contains the convex combination of such distributions, meaning that it contains also all distributions assigning probability p to the first one and probability y minus p to the second one. And considering convex sets is not just interesting from a theoretical point of view because it gives us a monad, but it's also interesting from a more concrete point of view since it accounts for probabilistic schedulers. So the idea that a scheduler that chooses between different non-deterministic transitions can also choose to probabilistically combine such transitions. So as we said, when we take convex sets of probability distributions, we have a monad. The monad of convex sets of probability distributions has a functor associating to a set X, the set containing all the sets of finitely supported probability distribution over X that are non-empty, convex closed, so that closed under convex combinations of such probability distributions, and finitely generated, meaning that such convex sets can always be obtained as convex combinations of only a finite number of probability distributions. As a unit of this monad, we have function assigned to X, the singleton containing the probability distribution assigning 1 to X. And as a multiplication, we have a function that takes a set delta 1, delta n of probability distributions over convex sets and returns the union of the weighted Minkowski sum of such probability distributions. And the weighted Minkowski sum is a well-known operation which, given a distribution over convex sets, returns the set of distributions that are given by choosing an arbitrary element for each of these convex sets and then weighting it with the weight given by the distribution in the set. And now that we have a monad combining non-determinism and probabilities, we can wonder what is the equational theory corresponding to this monad. And for the monad of convex sets of distributions, we indeed have an equational theory presenting the monad, which is the theory of convex semilattices. This theory has a signature, the signature of semilattices, so the non-deterministic plus, and the signature of convex algebras, so all these probabilistic pluses. And as axioms, as the axiom of semilattices, the axioms of convex algebras, and the distributivity axiom, which basically tells us how the probabilistic plus distributes over the non-deterministic plus, and which allows us indeed to derive convexity. And the presentation of this monad using convex semilattices was proven in recent work with Filippo Bonchi and Anna Sokolova, and we have applied it to verifying trace equivalence of label transition systems combining non-determinism and probabilities. But now we want to move, as we said, from program equivalences to program distances. And for doing so, we need to move from monads on sets to monads on metric spaces. So first, we are moving from the category of sets to the category Met of metric spaces, which is the category having as objects metric spaces, so pairs given by a set and a distance on pairs of elements of the set, and having as morphisms functions between such metric spaces that are non-expansive. That is to say, functions on the sets which do not increase the distances. And now, when we have a monad in the category of sets, we can try to lift it to a monad in the category of metric spaces. And when we do so, we will have a functor that associates a metric space xd here to the metric space having a set, the set of elements given by the monad over x, and then as a distance, the distance obtained by lifting in some way the original distance d to the set of elements of the monad over x. And then as a unit and multiplication, we can use the same unit and multiplication of the monad in sets, but we will have to prove that they are non-expansive. And if we can do so, we have lifted the monad from sets to Met. And indeed, this is something that we can do for the monad of convex sets of distribution. If we take the monad of convex sets of distributions in set, we can lift it to a monad on metric spaces by defining a functor associating to a metric space xd, the metric space having a set, the set of convex sets of distributions over x, and as a distance between such convex sets of distributions, the Hausdorff lifting of the Kantorovich lifting of the original distance d. What does this mean? Well, we start from some distance d between the elements of x, and then when we have probability distributions over such elements, we can lift the distance d to a distance between probability distribution using the Kantorovich lifting. So the Kantorovich lifting of the distance gives us a distance between probability distributions. And then, when we have a set of such probability distribution, we can use the Hausdorff lifting to compare such sets. And so, the Hausdorff lifting of the Kantorovich lifting of the distance gives us a distance between sets of probability distribution. And here it's actually important that such sets of probability distributions are convex and finitely generated, as this gives us compactness, which is needed in order to apply the Hausdorff lifting. And so this is the way we define the functor of our monad in Met. And then we have the unit and the multiplication, which are defined as for the monad of convex sets of distribution in set, but that we have to prove to be non-expansive, and indeed this is what we have explored in recent work together with Matteo Mio. And now that we have a monad on metric spaces, we can try to reason equationally about this monad, and to do so we can use quantitative equational theories. The framework of quantitative equational theories is a framework recently introduced by Mardare, Panangaden and Plotkin, which allows us to move from equation to quantitative equations, so equations between terms that now are endowed with some quantity epsilon that denotes that the two terms are at distance at most epsilon. Then we have quantitative inferences, which tell us how, given some distances between variables, we can derive distances between terms possibly containing such variables. And so, given a signature and a set of quantitative inferences, we have a quantitative equational theory, and from a semantic point of view, the models of these quantitative equational theories are quantitative algebras, that is, algebras endowed with a metric and satisfying the quantitative inferences in the theory. And formally, we have that the quantitative equational theory is a presentation of a monad on metric spaces if we have an isomorphism, again, between the category of Eilenberg-Moore algebras for the monad and the category of quantitative algebras or models for the quantitative equational theory. And now we can study specific quantitative equational theories that present monads on metric spaces we are interested in. And indeed, if we take the monad of convex sets of probability distributions on metric spaces, we have a presentation given by a quantitative equational theory of convex semilattices, which is the theory that has the signature of convex semilattices, so the non-deterministic plus and the probabilistic plus. And as quantitative inferences, we have first of all the axioms of convex semilattices, where an axiom is now embedded in the quantitative equational theory by transforming it into the quantitative axiom assigning distance 0 to the terms. And then we have two inference rules. The first inference rule is a quantitative inference that was already known from the work by Mardare, Panangaden and Plotkin to correspond to the Hausdorff lifting somehow. And this rule tells us that whenever we have some distances between terms and we compose the terms using the non-deterministic plus, then the distance of the composed terms is at most the maximal distance between the variables. And the second rule is again a rule that was already known to correspond to the Kantorovich lifting, and that tells us that whenever we have some distances between variables and we compose the probability distributions over such variables, then the distances between such probability distributions is bounded by the convex combinations of the distances of the variables using the same weights. So we have proved that the quantitative equational theory of convex semilattices is a presentation of the monad of convex sets of distributions on metric spaces. As a corollary of this presentation, by looking at three algebras, we obtain a representation result, which tells us that if we take the metric space having a set, the set of convex sets of distributions over X, and as a distance, the Hausdorff lifting of the Kantorovich lifting of the distance, well, this is actually isomorphic to taking the set of terms of the signature of convex semilattices modulo the axioms of convex semilattices, and as a distance, the distance given by the quantitative equational theory, that is to say, the distance assigned to any pair of terms or to any pair of representatives of the equivalence classes, the minimal distance that we can derive in the theory between such terms. And so this gives us a way to reason equationally about programs combining nondeterminism and probabilities and about metrics on such programs. Well, I hope you enjoyed this talk and thank you very much for listening.